Hello, everybody. Glad to see you can make it. Nice to see you again, Glory.
Nice to meet you.
Okay, and Brenda, I see Caldrian, Boots on there, Raimundo, Piera. Okay, cool. We got several others that will be joining us in a moment. So for those of you who are online, we've combined this with our on-ground Masters in Biotechnology students. So you guys get a chance to meet all of each other. I think that's a great opportunity. Because you're both going to be entering the workforce at about the same time. So one of the things about biotech is careers have a lot to do with networking. So the folks that you meet now that are kind of in the same cohort, we're going to be going on and doing cool things. And if you keep in touch for years and years, you may discover that you get lots of different opportunities with each other. Um, so something to consider. I'll wait for a second for everybody to get on. I see Neil's there. And if people can keep on their cams, it's really helpful for me when I'm teaching to be able to see that you're there. It's kind of how I work attendance. Um, in my undergrad classes, some people will sign on and then just disappear. They'll walk away from the room. Hi, Ariana. So keep your cams on. I'm going to try and make this semester fairly interactive, although there's lots of information to get through. So we'll see how that goes. I'm always open to feedback. So if you've got some issues with the format or anything else, or you just don't understand something, reach out to me. I will work with you one-on-one to make sure that you guys understand what you need to understand. So cool. Okay. I see Ernest has joined us. Okay. Let's see. Give just a minute for a couple folks. I think we have a total of 14 in our class. And I know one person couldn't make it today, but that's the nice thing. We're going to record all of this and it will be placed on Moodle. And to that end, for those of you, shoot me in the chat if you still can't get into Moodle, let me know. Because I want to make sure everybody can get there. I know, Gloria, you were having some issues with Moodle. I sent your request down to IT so they can give you a different way to sign in. But for any other folks, if you still can't find the 502 on Moodle, send me a little text in the chat so I know, because I want to make sure that you're all settled with that. Cool, we got more folks. This is great. I'm excited. I love teaching this class, by the way. It's designed it myself. It's based on courses I've taken at Johns Hopkins and University of Wisconsin-Madison and Penn State. I try and keep it as up to date as possible, which is why there isn't a textbook. We're going to be reading a lot of papers and doing a lot of hands-on stuff to try and keep everything current. So I'll teach you everything you need to know in the lectures, but we will need to take a lot of notes. And I think last time I talked about all these different kind of teaching pedagogy kinds of things that we'll try and do to keep everybody on board. And one of them is class scribe. So what I'd like is for one of you to volunteer. Everybody's going to have to do it at least once. You'll probably end up doing it twice this semester. But if somebody could volunteer to take notes for the class, and then after class sometime today, you'll just go up on Moodle and you'll go to notes of the class scribe, and there's a little discussion board there, and you'll just start a new discussion. You'll put today's topic as the title, and then you'll just upload your notes there. And I give out extra credit for people who add on important, relevant details to the notes. And so that's always a good way to keep involved and see what's going on. If you're not a great note taker, usually it's a good way to get additional notes. And if if you're the class scribe, you'll end up doing a better job because you're motivated, because you know the rest of the class are going to be looking at your notes. Um, uh, with that said, the other thing I wanted to mention was don't forget in the getting started page, if you've gone on to Moodle, there's a getting started page. There's a couple things you need to do. One of those is to to sign on to the flip group for the course. And then there's an introduction video, 2 to 3 minute introduction video that you'll record of yourself, kind of introducing yourself to everybody else. I know that all the online folks have done that last semester, so you all know each other already, but this is for the rest of the class to get to know you as well. And so everybody's going to do it. I know that Caldrian's already turned his in. I saw that one. And so I'm looking for more. That'll be great. And then that kind of gets us up to speed. Um, I had an email from 2 students that are going to be gone on Friday because of a conference. That's cool. Make sure that you, before Monday, get online and watch the videos from Friday, because on Monday we'll probably have a little quiz about what we talked about on Friday, and you'll want to be up to speed with, what kind of assignments there are. One of the things I found with this course, since we have to cover so many different topics, or in depth, is that it moves at a different pace depending on the students in the course. So I can't always predict ahead of time what we're going to get to by the end of the week. I just know the order of assignments, so I'll assign stuff as we go and try and keep you alerted to that. Any questions before we get started? Okay, cool. Like I said, folks, if you can turn on your cams, that would be great. Kayla, Eugene, it's really important we all try and be present. I'm going to go ahead and share my screen out of this jacket because it's so cumbersome. It's too hot in here. Okay, that's a little bit better. Gonna need a little work. Okay, so there. Okay, so first off, who will volunteer to be the class scribe today? Can I get somebody to do that? Caldrian? Okay, thank you so much. I appreciate it. I see your hand up. So for that, take a note of the main points. I'm going to post all the PowerPoints up on Moodle, so you don't have to copy what's in the PowerPoints, but jot down what you think, main take-home messages are. Always note what the quiz question is, because you'll find that the most important stuff I always ask over and over again. So if it comes up as a quiz question, you'll see it on a problem set, you'll see it again on an exam, and then you'll see it again on the final. So that's usually really helpful. Okay. And sometimes I'll ask for other volunteers if the class scribe of that day can keep track of who's volunteering for what. And we may do stuff in breakout rooms, like if we have contests and stuff like that, and the class scribe will normally keep track of, who wins the contest, so I know who to give points out to. So one of the places I want to start is what I promised with before is to start with a quiz. I almost start every class, beginning of class, with a quick quiz. Obviously, we only covered certain stuff last time, but I almost always do the quizzes based on, what we did last class. So when you're right before class, when you're getting ready for it, you might go over, the notes from last class, go over the PowerPoint, and that'll probably put you in a good situation for the quiz. And so the way we're going to do this is, let's see, let me put in the chat. I am going to paste a link to a form. If you just click on that, it's a pretty simple question. What are the 4 main themes or overarching principles of the course? Now, these quizzes aren't worth a lot, so don't stress if you don't know it. If you missed last, if you missed last lecture, it's no big deal if you don't get a decent grade on the quiz, because it's 10 points out of like 3,600 points for the course. It's just in general, if you don't do well on a lot of them, that could affect your grade. But 1, 2, 3 quizzes missed, 4 quizzes missed isn't going to make much of a difference at all. So don't sweat it. But do your best. So what are the 4 main themes or overarching principles of the course? I'll give about 4 minutes to answer this.
Yeah. Hmm?
Okay, so far I already got 3. And what's neat is I can see them as they come in. About 2 more minutes. Your best recollection of what we talked about last time. Just another minute. You should be close to hitting enter and sending in your responses. Well, good. I'm seeing some good responses here. This is great. Okay, nice. 20 seconds.
My link not coming up, Dr. Panasik.
Oh, it's not? Let me try.
Like I'm selecting it, but it's not opening options.
Oh, I don't know why. Well, no worries, because I'm about to close it down now anyways. Did you manage to open it, Kamani? You
I
could
still
just
not look.
you could just type it in the chat, but just send it directly to me.
No problem.
That works too, if necessary. I just have to remember to look back there. Okay. So be a second there, Kamani, to send that real quick. So it looks like I got just about responses from just about everybody, which is cool. Um, so let's start out with what can somebody say what are the give me one of the main themes? What did you guys put down?
Functions and everything start with binding and unbinding.
Yep. Or just about all events start with a binding or unbinding event. So binding is key when you talk about any kind of process. What else do we got?
Structure determines function.
Structure determines function, how something's shaped, what atoms are a part of it, what particles make up the compound, determine how it's going to act. What else do we have? It's funny because some of you put it in your answers. So here's the four. Structure determines function. Energy differences drive events. So it's differences in energy that causes things to happen or not to happen. And then these events are mediated by the binding and unbinding. And then finally, it looks like that's the one that most people had struggled with the most, is that all the different structures exist in an ensemble of different forms. And do you know what I mean by ensemble? So think of, well, when you hear the word ensemble, what do you guys think of?
I think of like
Group.
when they say ensemble cast, like big
Uh-huh.
important factors, a large amount of important factors.
So, like you often hear it like an ensemble cast, or an ensemble might be a group of instruments that are going to play at a musical thing. And so one ensemble might have like 10 trumpets, a few flutes, and some drums, and a variety of instruments. A different ensemble would have a different collection of instruments. And so an ensemble is just a grouping of things. An ensemble cast is just a grouping of actors, usually big name actors, when they say an ensemble cast. And so an ensemble is just a specific set of stuff. And so when we talk about structural shapes or conformations, or the way it's structured, like whether it bends to the left or bends to the right, if you had 1,000 molecules, some of them will be bent to the left, some of them will be bent to the right, some of them won't be bent at all. That's your ensemble, and that ensemble exists proportional to its energy. So things that are high in energy don't exist very often. Things that are low in energy exist all the time. And we'll talk about this quite a lot when we get to Boltzmann and we start talking about energies. But just remember, low energy things are more common than high energy things. But all things exist in kind of a grouping where there's lots of different forms of it. You'll see more of the lower energy forms than you will the high energy forms. And so those are our main principles in the course that we'll see over and over again. And we're going to use this as like a common language to understand everything else in the course. So it's always challenging for me to figure out where to start in this course because there's lots of different ideas. So I'm going to try and start with something simple. I want to see if this new camera is going to work. So let me try this. And okay, I think that's on. Can you all hear me? Okay, great. So let's see if this is going to work. The way this is going to work, I'm going to ask you questions and you're going to put them in the chat. And I'm going to ask you some questions pretty quick. I like everything to be really interactive. And we'll start with something simple like, what is your age? Go ahead, type that into the chat, make it visible for everybody. And we'll go from there. Let me go ahead and put up the first question on a slide. Okay. Can you see that? Okay.
So, you know how old you are. How long have humans been around? Okay, how long has life existed on Earth? How old is the Earth? Okay, how old is the universe? In actuality, the universe is 13.8 billion years old. The age of the Earth, 4.5 billion. Life's been around for about 3.5 billion years, as far as we can tell. Multicellular organisms probably appeared around 600 million years ago. That's about it. And the first humans probably about 200,000 years ago. We only have about 5,000 years of recorded history. So when I'm talking about the early universe, its very beginnings, 13.8 billion years ago, that's a long, long, long time ago. And so it's at this point that I want to start here. Let me move out of the way and get back. Okay. Let's see. So at this point in time, all energy, all matter, and all space in the universe was compacted into a single subatomic particle. Everything you know, everything you don't know, the molecules in your hands, every atom in this room, every atom in every room, everywhere, the planets, the sun, the stars, our galaxy, the hundreds of billions of galaxies in the universe, all of them condensed into one small, tiny particle. A point in space, smaller than a subatomic particle, smaller than an atom, with a temperature of an anillion degrees centigrade. It's this tiny little dot. Tiny, tiny little dot. Ultimate order. And in that moment, or in a moment, actually time didn't exist then, there was an explosion. And from this tiny dot, all of the universe started to expand. In a billionth of 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 a second, it went from the size of a tiny subatomic particle to the size of our known galaxy in that much of an instant. The point I'm trying to get across is that our universe started from a point of super high energy. All of the atoms were in one place, so we knew exactly where they were. There was no disorder, there was no confusion, because everything was in one place. We call that a point of ultimate order. It's also a point of ultimate energy because the energy was the highest it's ever been in the universe. Over an anillion degrees centigrade, energies that we really can't calculate anymore. And so the energy of the universe starts out super high. And when it explodes, the energy starts dispersing, space starts to expand, things start to cool down, and the energy in the universe goes lower and lower and lower and lower over time. In fact, it's starting at this high point of energy and going to a lower point of energy that gives us a direction to time, knows us what's in the past, and tells us which way is the future. The universe is always going from high energy to low energy. And it's this fundamental concept that's going to take into account all of what we're going to talk about in biochemistry class. This introduces the concept of Gibbs free energy. Put that up over there. Okay, you've probably seen this equation before in your chemistry class, probably. Delta G equals delta H minus T delta S. Delta G stands for Gibbs free energy. Delta H is the enthalpy, T is temperature, and delta S is entropy. So what is enthalpy? What's delta H mean? Change in enthalpy. What is that?
Hmm.
How would you describe enthalpy?
Hmm.
So you can
oh,
think of energy, enthalpy as the energy within bonds. Okay? When you have a strong bond, there's lots of energy in that bond, it's a high enthalpy. Entropy is something very different. It's randomness. The more random things are, the more entropy you have. If you've got 3/4 and they're all heads, that's one state of order. If you start mixing them up and they become disordered, that's an increase in entropy. And this equation is going to determine what happens in our universe and what doesn't happen in our universe. Okay? So enthalpy is like the energy released when a bond is formed. Entropy is disorder. The higher the entropy, the more disorder you have. Okay? So an ordered system has higher energy than a disordered system. So think of the Big Bang. Right before the Big Bang, when you had that single point, that was infinite amount of order because all the points were in the same place, all particles were in the same place. And so that was an infinitely ordered system. And then as the universe expanded, it got cooler and cooler, lower and lower energy, and more disorder. So order, high in energy, disorder, lower in energy. That's a key thing we have to understand. Free energy changes can predict the direction of a reaction, whether it happens or not. If your delta G is negative, if all these terms come up to a negative number, then that means the reaction is just going to happen spontaneously. You don't need to do much to make it happen. Things go from high energy to low energy without much of an issue. So if you're talking about a reaction of any kind, you just look at the beginning state and the next state and see whether is the beginning state higher in energy or lower in energy than the next state that you're looking at. If the beginning state is higher in energy and the next state is lower in energy, that reaction is probably going to happen spontaneously. And it's just the way the universe works. Things go from high energy to low energy. If I've got this little remote control, hopefully it won't break when I drop it. Up here in this gravitational field, it's high energy. When it gets lower, it's lower energy. So if I start with it up here, let go of it, I didn't have to do anything and it didn't break, but it drops down to the ground. It goes from high energy to low energy. Now, if I want it to spontaneously go from low energy to high energy, I love doing this demonstration. It's not going to happen. I can wait here for the rest of my life. That thing isn't going to jump off the floor and into my hand. And I have to pick it up. So we're going to use this concept of free energy to is the common language throughout the rest of the course to help us understand when things are going to happen and when they're not going to happen. And to do this, we're going to be drawing what we call free energy diagrams. So I'm going to show you how to draw a free energy diagram. First, you're going to start out with, let's see if I can do this. You're going to start drawing a line for the x-axis, line for the y-axis. We'll put in delta G over there. And on the y-axis, we'll type in reaction coordinate. And this is important. You'll need to put in a line for your initial state. That initial state's going to have some amount of energy. And you want to make sure to label this initial state. If it's a ball on top of a hill, you'll write down ball on top of a hill right below it. If it's your reactants, you label reactants.
Don't just always put reactants. If we're talking about a physical process, I want to know what state you're starting with and what state you're finishing with. And the next thing you do is you draw your second state. If you're going from high, you have to figure out, you have to determine, are you going higher in energy or lower in energy? If you're going in lower in energy, you draw a line that's lower, and then you'll end up drawing a line, a little curve in between the two that has a hump. Okay, it looks like that. This distance, the distance between the two energies, so if you were to draw a line like this and like this distance here, from here to the very bottom there, that's your delta G. And then this distance here, this is the height of the hill you have to climb. That is your delta G double dagger, or your activation energy. So this is delta G. We put these two lines through there, that's delta G double dagger. And this is your standard delta G. And that's what a reaction looks like going from high energy to low energy. Now, if by chance you're going from low energy to high energy, things look a little bit different. You'll write your second state as being higher in energy over here like that. And then when you draw your line between the two, it'll be something like that. It'll still have a hump. And it's still true that the distance, the difference in energy between these two states, so between state 1 and state 2, this distance here, that's going to be equivalent to your delta G. And now for your delta G double dagger, your activation energy, remember it's the height of the hill you have to climb to get to the other side. So for here, you've got to go over this whole hump to get to the other side. So your delta G double dagger goes all the way to the top. And this is your delta G double dagger. In either case, this little point up at the top, that is your transition state, or we call it TS for transition state. So when you're drawing your free energy diagrams, remember you first draw an L, you label your y-axis as delta G, your x-axis is the reaction coordinate. Then you'll draw a line for your initial state. Remember to label what you were thinking of as your initial state right below that line, and then figure out what your second state is, whether it's higher in energy or lower in energy, and then you draw a little hump in between. The difference between the two energy states is always going to be delta G, whether it's higher or lower. In this case, it's a positive number because you're going up, and if you were going to a lower energy, it would be a negative number going down, so delta G would be negative. If you're going higher in energy, remember that your activation energy, or delta G double dagger, is always the height of the hill you have to climb to get to the other side. So in this case, it's way up here. If you're going from a reverse case, where it's lower in energy, it's only the height of the hill that you have to climb to get to the other side.
So what was the first principle that we talked about when we said structure determines function? Can everybody say that out loud? Structure determines function. Oh, come on, you guys can do it better than that. Louder. Come on, let's engage. Structure.
Determined function. Determined
Okay,
function.
good.
Good.
So if we're starting
Structure
from the beginning, let's start with atoms and their structures, since we're going to be building everything from atoms. And it's going to be the subatomic structure of an atom that determines its properties and its functions. Okay. And so to start out with, we're going to bring up where electrons go around an atom. Okay, so this is an old depiction of what people used to think atoms were like. They've got a nucleus in the center, and what's composed in the nucleus? What particles are in the nucleus?
Protons and neutrons.
Mm-hmm. Okay, and then circling around that, they would say are what? Okay, that's totally not the way it is. What we've learned from modern quantum mechanics is that electrons actually don't orbit the nucleus like planets orbit a sun. They exist in an area, okay, that we call an electron cloud or an electron shell. Depending on how close they are to the atom and their energy levels, depends on the shape of what that space looks like. So we call these things orbitals, okay? And an orbital is defined as a region in space where you have a 95% chance of finding an electron, okay? And so over here, this is what we would call an s orbital. That's the lowest energy level, and you'll find a 95% chance of finding electrons in there. And each orbital can only hold 2 electrons. You got to remember that. 2 electrons. Can everybody say 2 electrons? Okay, I promise all this will pay off later on. It'll help you remember, hopefully. So after if you've got an atom that's got more than 2 electrons, you have to go on to another orbital. So after the first s orbital, there's what we call the 2s orbital. That's also spherically shaped, and that's a 95% chance of finding those electrons in that region. And then if you have more electrons in that, they're going to be in a higher energy orbital called the p orbitals. And there's actually 3 p orbitals, as you can see here. They're barbell shaped. So quantum mechanics gives us shapes of these orbitals. And as you can see, there's a barbell that's oriented up and down, sideways, and then in and out. And so we call them the px, the py, and the pz orbitals. And so if you've got an atom that's got, say, 5 electrons, what orbitals would they be in? Remember, you always start filling electrons in the lowest orbitals first. So you'd have your first 2 electrons will occupy the 1s orbital. The second 2 electrons would occupy the 2s orbital. And if you had 5 electrons, the 5th electron would fill one of the p orbitals. And the more electrons you have, the more orbitals you start to fill. And really, for the most part, we're not going to need to go beyond the p orbitals, because in biochemistry, as you'll find out, 95% of biochemistry involves only 4 atoms: carbon, hydrogen, oxygen, and nitrogen. Sometimes we'll see sulfur, and sometimes we'll see phosphorus, but for the most part, it's hydrogen, carbon, oxygen, and nitrogen. That's 95% of all of biochemistry. So here's our different orbitals that we have to work with. One of the things I want you to be able to do is, if you're given an atom and told how many electrons are in that atom, you should be able to populate the orbitals and tell me how many, what the electronic structure is and how many electrons are each of the orbitals. Okay. And here's where we combine 2 concepts. So we talked originally about free energy. So let's talk about the free energy of electrons and their orbitals. It just so happens that an orbital is lower in energy if both of the orbitals, if the electrons are, an orbital is lower in energy if it has 2 electrons instead of 1. 1 electron, higher in energy; 2 electrons, lower in energy. Okay? And remember, we were talking about the 1s and the 2s? Well, the 1 and the 2, those stands for valence shells. And when you complete all the orbitals in a valence shell, you're also lower in energy. So when you complete the 1s orbital, since there's only an s orbital in the one valence shell, then you're lower in energy than if you hadn't. The second valence level has an s and the p orbitals. So if you fill all of those, you're all of a sudden lower in energy as well. And so that's going to lead to what we call electronegativity, okay? Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. In other words, it's the pull that the atom has on the electrons. Why do we say it's a pull? Because if an electron goes from one place and then jumps onto the atom and it happens spontaneously, if it happens faster, more spontaneously, it has a greater pull. What makes things spontaneous? What do we say makes things spontaneous? If the delta G is negative, right? So if you're going from high energy to low energy. So if you're filling an orbital, you're becoming lower in energy. If you're filling a valence shell, you're becoming even lower in energy. And so that helps determine all of chemistry. So if you look at the periodic table, hydrogen on that side, see helium over here. Hydrogen has one proton, which means neutral hydrogen has one electron. So it doesn't have its valence shell filled, but helium does, right? It has two electrons, fills the s shell, the s orbital, and that fills that final valence shell. So it's completely happy. It's a lower in energy. That's why it's in this column over here. You'll see the same is true about neon. Neon has all of its electrons filled, okay? It has 20 electrons, so that's going to fill all of its orbitals. And so it's not interested in getting any more electrons. So it's not going to interact with anything. It's not interested in giving up electrons because it's happy where it is. And so it's going to make no bonds. In fact, all these atoms along this row of the periodic, or this column of the periodic chart, have their final valence shell filled. And so they're going to be chemically inert. They're not going to want to react. But look at fluorine. Fluorine is one away from filling its final valence shell. That means it really wants one electron. And so what's it going to do? Spontaneously, if it can, it'll pluck an electron from somewhere else. Yeah, it'll become, it'll have a positive charge, but it will have completed its valence shell. Unless it can share that electron. And so that's what atoms do. Let's look at hydrogen, for example. Hydrogen has one electron, one proton, and one electron. What does it need to fill its S shell? Right, so it only needs one electron to fill its S shell. So what if you were to put two hydrogens next to each other, really close? Now it can form an orbital that fits around both of those nuclei. So there's one orbital. It's now got two electrons. So each hydrogen nucleus has its orbital filled. It's lower in energy. And what does that make? That's H2, or hydrogen gas, and that's something you find naturally in the environment. Let's look at something else that you know. Okay, so back over to fluorine. How many electrons did it need to fill its final valence shell? So if it was to be put next to something else that had just one electron to share, like hydrogen, and you had one orbital around both of them, now both hydrogen and fluorine have an orbital, an s orbital around its, or an orbital around its nuclei where the valence shells are full. And it's completely happy. That leads to HF. So fluorine will always want to make one bond because all it needs is one electron. What about oxygen? How many electrons does oxygen need to complete its final valence shell? You can see fluorine needed one, oxygen needs two, right? Nitrogen would need three, carbon would need four. So oxygen needs two electrons. So let's say you had two hydrogens close by. We'll put one on either side. those will start to share. Now oxygen has its final valence shell filled, and it has formed, what's that molecule? That's why water exists in the form of H2O, 2 hydrogens, 1 oxygen. Now, if you look at carbon, how many bonds does it need? It needs 4, right? And so carbon will always make 4 bonds, nitrogen will always make 3, oxygen will always make 2, fluorine will make 1, but we don't need to worry about fluorine because remember I told you really the only atoms we're going to be worried about are carbon, nitrogen, oxygen, and hydrogen. How many bonds does hydrogen make? Throughout the course of the semester, I'm going to be having you draw different compounds. And when you draw them, make sure to count up the number of bonds on each of your atoms. Hydrogen should only have 1, oxygen should have 2, nitrogen should have 3, and carbon should have 4. And so remember that. So we see how all of modern chemistry comes from orbital theory. We also see where electronegativity come from. You'll see on this electronegativity chart, it's showing fluorine is very, very electronegative because remember, it just needs to pull that 1 electron over and it's completed its valence shell. So it's got a really strong pull. Oxygen is a close second in terms of electronegativity because it's really close to filling that valence shell. It just needs 2. And then nitrogen's even very electronegative, as you'll see it's in yellow. It just needs 3 and then it's done. By the time you get to carbon, well, it needs 4, and that's valence shell would be filled with 8, so it's about halfway to the end, halfway from the beginning. It would be just as happy losing some as it would be gaining some, so it's not really electronegative at all. Same thing with hydrogen. It's not very electronegative at all. It could lose an electron and just become a free proton or an H+, those are common. And so remember, carbon and hydrogen are not electronegative, while on the other side, fluorine's the most, then comes oxygen, then nitrogen, and if you want to throw sulfur and phosphorus in there, you can, and then finally carbon and hydrogen have almost no electronegativity. Okay. So now we're going to get to polar bonds and sigma and pi bonds. So a sigma bond is just what we saw with the hydrogen. It's basically when it's a covalent bond, so it means there's going to be sharing of electrons. And so it's when 2 nuclei get close enough together and they basically share an orbital around them to complete their valence shells. Okay, that's your sigma bond. It's what we would call like a single bond. So if you see a carbon-carbon single bond, that's a sigma bond. Then come the pi bonds. Now remember those pi orbitals, the ones that look like barbells? Those 2 will come together, both on the top and on the bottom, and those 2 will form a bond. And so you'll see when you have a pi bond or a double bond that you have sharing above and sharing below. Remember how these can be, your pi orbitals can be in the x direction, the y direction, or the z direction. So there's going to be an up and a down, or you can put it sideways, but there's always going to be a dichotomy from where they are. This is going to make it so you can't turn or you can't rotate in a pi bond, but you can in a sigma bond, as you can see here. If you were to try and rotate those 2 nuclei, you'd have to break the pi bond above and below in order to get some rotation. Whereas in the single bond, you can just freely rotate. Okay. And so finally, what that's going to lead, when you have 2 atoms that have the same electronegativity, they're going to share those electrons and those orbitals equally, like you see here. That could be a hydrogen and a hydrogen, or two oxygen molecules together. Remember, an oxygen needs 2 electrons, so does another oxygen, and that's why you get O2. But if you pair together 2 atoms that have very different electronegativities, where one's stronger than the other, then you get an unequal sharing of electron density in their orbitals. And you'll start to pull electron density towards one and kind of leave the proton exposed on the other side. And so when you have one of these polar bonds, that means you got more electron density on one side, so this side is going to be partially negative, and on the other side, it's very de-shielded, or you have a lot less electron density, and so it's kind of like that proton butt is kind of hanging out at the end, and so you'll have a partial positive on that other side. And that's going to be really key when we get to forming hydrogen bonds. And that's where we'll stop now. But tomorrow we'll talk about the structure of water and how it has polar bonds and what that leads to. Thank you. Okay, let me switch back.
Questions? I see some head shaking, lots of stuff. Okay, just to break it down, 3 main points. Things go from high energy to low energy spontaneously, right? That's how the universe started, was high energy, and it spontaneously has been going to low energy, and it's going to keep doing that. So things are always going to lower and lower energy. When you put together an atom, if you've got 1 electron in an orbital, it's higher in energy than if you have 2. And so that means spontaneously, atoms are going to try and fill their orbitals because they're lower in energy when they do that. And so spontaneously, they're going to share somebody else's electron, and spontaneously, they're going to form these covalent bonds, either single sigma bonds or double, a double bond that's got a sigma and a pi bond. And some that are really close to filling their valence shell are going to pull a lot stronger than those that have a long way to go in filling its valence shell. And so oxygen and nitrogen are going to be 2 that are very electronegative, where carbon and hydrogen aren't. Those are the 3 takeaway messages I'd say out of this. Things go from high energy to low energy. Remember how we were drawing those free energy diagrams? And then orbitals are lower in energy when they're filled. Same thing with valence shells. And oxygen and nitrogen are very electronegative. Hydrogen and carbon aren't. So it's a lot. We'll unpack it next time if you guys want. I want to move at a pace where everybody's on board, so we can start next time with questions. I'm curious about what you think the next quiz might be about, but it probably would be on one of those 3 things. I would definitely know your free energy equation, Gibbs free energy equation, delta G equals delta H minus T delta S. While we're not going to be doing a lot of math in this course at all, understanding that equation and how it works is going to be pretty important, even though we're not going to be doing a lot of math or anything. It's the relationships in that equation that are important, because that's a negative T delta S, and that's important. But we'll talk about that next time. No questions? We're all good? Kayla, Kamani, Yara, Neil, Amungo, Caldrian, you seem to be good. Okay. Okay, great, guys. Have a great day. And sorry if I overwhelmed you on this first one. How do you like my little gizmo?
I think it was good.
Okay.
Yeah.
Okay, cool. We'll see if I can't keep that working. I'm still trying to play with technology a little bit, but I'm trying to spruce things up so it's not just a boring PowerPoint lecture, but we'll see. Okay, guys, have a great day. Talk to you soon. Bye-bye.